The James Webb Space Telescope, JWST, has made a truly astonishing discovery. Beams of light that appear to radiate from what could be an urban center located light years from Earth. This extraordinary observation has reignited global interest in the search for extraterrestrial life, focusing its powerful infrared instruments on Proxima Centauri B, the closest known exoplanet to our solar system. The telescope detected strange, intense flashes of light. Could these signals be evidence of an alien civilization? The possibility is electrifying. For decades, both scientists and the public have been captivated by the idea of life beyond Earth. Every hint of potential life in outer space is met with excitement, but this moment stands apart. The JWST's findings offer perhaps the clearest evidence yet of something extraordinary, a potential alien metropolis lighting up a distant world. As the telescope scanned the vast darkness of space, it detected light patterns resembling those of terrestrial cities. This discovery has sparked tremendous curiosity within the scientific community, suggesting the presence of intelligent life, perhaps even civilizations operating in ways we're only beginning to comprehend. The city-like lights were spotted from a staggering distance of over 4 light-years away, astonishing NASA engineers who wonder how long they've been visible, simply waiting for our technology to catch up. Astronomer David Kipping of Columbia University noted the unique behavior of the planet where these lights were observed. Unlike typical rocky planets that absorb sunlight and emit it as infrared radiation, Proxima Centauri B behaves differently due to its complex interaction with its host star. This unusual energy pattern was key to the discovery and showcases the immense power of JWST. Thanks to its sensitivity to infrared wavelengths, the JWST was able to detect these unusual emissions and shed light on the atmospheric conditions of Proxima Centauri B. Researchers now plan to continue their investigation, aiming to determine whether the planet might be habitable. Most telescopes struggle to detect faint light sources in the darkness of space, but the JWST excels in this domain. Its ability to pick up subtle glimmers makes it an ideal tool to verify whether the supposed city lights on the night side of Proxima B are real. The telescope can detect artificial light, but only if it falls within a specific frequency range, much narrower than the broad spectrum emitted by natural stars. Proxima Centauri B also shares a dynamic relationship with its parent star. Like many exoplanets, it undergoes cycles of day and night. These shifts in exposure to its star's intense radiation create extreme temperature differences between its two hemispheres, scorching during the day, freezing at night. If the planet has an atmosphere, this thermal contrast would be even more pronounced, offering critical insights into its composition and structure. The James Webb Space Telescope, with its advanced infrared imaging capabilities, can observe these thermal emissions and provide detailed data on the planet's atmospheric behavior. Notably, the timing of JWST's Earth orbit allows scientists to observe Proxima Centauri B's daylight cycles, which occur every 11.2 Earth days. If it turns out that Proxima Centauri B does have an atmosphere, the next phase of research will focus on analyzing its chemical makeup. Detecting key elements, such as oxygen and water vapor, would be a monumental step forward in confirming the planet's potential to support life. The presence of gases like methane could indicate a planet's potential to support life. Detecting such gases involves analyzing the light that passes through a planet's atmosphere, a highly complex process. While the James Webb Space Telescope, JWST, excels at examining atmospheric compositions, particularly the presence of water vapor, carbon dioxide, and methane, it is not optimized to detect free oxygen, a crucial biosignature. However, it can still search for other indicators like ozone, which suggests a stable, life-supporting atmosphere. As scientists analyze data from JWST, the search for habitable worlds continues, inching us closer to answering one of humanity's most profound questions. Are we alone in the universe? That said, JWST has its limitations. It can only observe a select number of exoplanets relatively close to Earth. For deeper and more detailed investigations of distant planetary atmospheres, astronomers will depend on next-generation ground-based observatories like the Extremely Large Telescope, ELT, expected to begin operations in 2027. The ELT will offer sharper, more detailed views of exoplanetary atmospheres, helping scientists better assess their habitability. While we await the ELT and future space missions, JWST remains a vital tool in the exploration of exoplanets, providing essential insights that continue to expand our understanding of the universe. Looking ahead, researchers are developing advanced space telescopes with cutting-edge technologies designed to block out the overwhelming light of stars, much like using your hand to shield your eyes from the sun, to better detect the faint light reflected by orbiting exoplanets. This is critical for atmospheric analysis and evaluating a planet's potential to support life. However, detecting such faint planetary light is incredibly difficult. Stars are vastly brighter than their planets, often outshining them by millions of times, making it extremely challenging to isolate a planet's signal. To overcome this, scientists are testing several promising innovations. Coronagraphs. These are instruments placed inside telescopes that block starlight while allowing planet-reflected light to pass through. By shaping incoming light waves precisely, coronagraphs can suppress stellar brightness and reveal the dim light from surrounding planets. Star shades. These large, flower-shaped spacecraft would fly tens of thousands of kilometers in formation with a telescope. By blocking starlight before it reaches a telescope, star shades allow only the exoplanet's light to be captured. This technique could be especially useful for observing planets in the habitable zone, where conditions might allow for liquid water and potentially life. These technologies require extreme precision. For example, aligning a star shade perfectly across vast distances must be accurate to within fractions of a millimeter. They must also overcome significant engineering challenges, such as minimizing size and weight, conserving energy, and surviving the harsh environment of space. Despite these challenges, the potential payoff is immense. If successful, future telescopes could detect biosignatures, chemical signs of life, such as specific ratios of oxygen, methane, and water vapor. These molecules, especially when found together, could suggest the presence of biological processes. Researchers are also pursuing direct imaging of exoplanets in greater detail. Future telescopes equipped with advanced adaptive optics, which correct distortions from Earth's atmosphere or telescope movement, could produce clearer, sharper images. When combined with starlight blocking techniques, these innovations could not only detect exoplanets, but also map their surfaces and reveal characteristics like cloud cover, oceans, or even seasonal changes. In sum, while the path is complex and filled with technical challenges, the progress being made in space telescope design and atmospheric detection techniques holds the promise of one day identifying life beyond Earth. The development of next-generation space telescopes marks a monumental leap in humanity's ongoing quest to answer one of our most profound questions. Are we alone in the universe? By significantly enhancing our ability to observe distant worlds, these instruments are bringing us closer than ever to uncovering whether life exists beyond Earth, potentially transforming our entire understanding of our place in the cosmos. The pace of space exploration and the search for extraterrestrial life is accelerating rapidly. As scientists and astronomers dig deeper into the mysteries of distant exoplanets, the James Webb Space Telescope JWST is leading us into a new era of cosmic discovery. The groundbreaking data it collects is shedding light on the structure, composition, and potential habitability of far-off worlds. With every new insight, we inch closer to answering that ultimate question. Is there life beyond our planet? One of the most compelling targets in this search is Proxima Centauri B, the closest known exoplanet to our solar system. Located within the habitable zone of its star, it has long been the subject of intense study. This region, where temperatures are just right for liquid water to exist, is a key indicator of a planet's potential to support life. Imagine vast oceans, flowing rivers, or even lakes beneath alien skies. Until recently, the idea of detecting artificial lights or signs of civilization on such a world remained in the realm of science fiction. But now, the James Webb Space Telescope has observed mysterious glimmers of light that suggest the possibility of artificial sources, reviving hope that intelligent life might exist elsewhere. This potential discovery has captured both scientific interest and public imagination, inspiring new generations to look beyond the boundaries of Earth. The JWST is not only searching for artificial illumination, but also studying exoplanet atmospheres in detail. By analyzing their chemical makeup, such as the presence of methane, carbon dioxide, or even ozone, astronomers can assess whether these worlds have the necessary conditions for life. Unlike any telescope before it, Webb can detect these vital biosignatures with remarkable precision. Adding to the intrigue, Proxima Centauri B may be tidally locked, meaning one side always faces its star while the other remains in darkness. This could create extreme temperature differences, raising questions about climate stability and the potential for habitable zones along the planet's twilight edges. Understanding such dynamics is crucial in evaluating the planet's ability to support life. Technological advancements are also revolutionizing how we study exoplanets. Tools like coronagraphs and star shades can block out a star's overwhelming brightness, allowing telescopes to detect the faint, reflected light from orbiting planets. These breakthroughs are critical for examining planetary surfaces, climate systems, and any signs of life. One of the most exciting developments on the horizon is direct imaging of exoplanets. Using adaptive optics and light-blocking technology, future telescopes may be able to capture high-resolution images of planets orbiting distant stars. These images could reveal surface features such as oceans, continents, or even weather patterns, offering an unprecedented view into the environments of other worlds. As our tools and methods evolve, so too does our ability to answer fundamental questions about life in the universe. The James Webb Space Telescope and the missions that will follow are pivotal in this endeavor. Their ability to detect faint planetary signals, analyze atmospheric conditions, and assess habitability is already reshaping our understanding of the cosmos. With each new discovery, we move closer to a future where the existence of life beyond Earth may no longer be a question, but a fact that redefines what it means to be human.